last week we looked at the controlled rectifier drives. So today we'll do chopper fetch drives. That's what we'll focus on today. So we'll do the 1 quadrant, 2 quadrant, and 4 quadrants. If there is time, then we will look at the controller design. So that is what we will be doing today. Okay. So let's look at the first one. So this is the diagrams we are seeing here basically represents um a 1 quadrant drive. So you see that this portion represents the motor. So the back EMF in the motor resistance and self-inductance. Then we have the switches, the BJT and then diode. So they are the power electronic converters. So we understand the operation, then perform some calculations on them. So let's go into the chopper drives. So the chopper drive is a chopper is a DC to DC converter. So it takes a DC voltage and then convert it to another DC voltage, a variable DC voltage. That is what we are doing. You take a fixed DC voltage and you get a variable DC voltage out of it. So they are using supplies for fixed DC supplies such as batteries and trams, power steering, robots, and overheads catenary. So these are some examples of fixed power supply. So they have fixed power supply. So it's advisable to use choppers there. So they are also used in places that requires fast torque control because they are faster than the rectifier control um drives. So that is what we can see because they have a high switching frequency. So you can switch them at higher frequency. So they are faster than your rectifier controller. So we look at 1 quadrant, 2, and then 4 quadrants. So the switches that are used are fast switches. So either you use MOSFET or IGBTs for the switching. Okay. So let's take note of these things about choppers. So the supply is fixed. So there is a fixed supply, which is a DC voltage. Then we usually switch at fixed frequency. Then we will vary the duty cycle, right? So the supply is fixed. We switch at fixed frequency, and then we control the output by varying the switching time, which is the duty cycle. And the duty cycle is given by the on time of the switch divided by the period. So this is the duty cycle. So let's take note of it. So the output voltage has a DC component and a large ripple component. So because of the switching, there will be ripples in the output, but it has a DC output and then there will be ripples. So, but this usually, the output that is obtained is usually fed through an inductive load like a motor. So when you have a motor, the motor has inductance. So the inductance will filter, will smoothing the current that will flow through its winding, right? So the inductance in the load is going to limit the DIDT, thereby the current is going to the current to be smoother than the voltage. So if we know that torque and then current are related. So if the current is smooth, that means that the torque too will also be what? Smooth, right? So IDC is large compared to the ripple component, so it is reasonable efficient because filtering has been done by the inductance of the load. So we vary the duty cycle to vary the mean output voltage. And for a continuous current, it is given by this. This is I think we've seen this in power electronics also. So for a continuous current, the output voltage, that is the mean output voltage, is given by the duty cycle multiplied by the input DC voltage. So this is the ideal control voltage source. So you are controlling the output by varying the duty cycle. Okay, and the output is what is fed through the 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 terminals of the motor. So we'll look at that soon. So these are the assumptions when you're dealing with the chopper drives. So the supply is constant. Switching is also, the switching period is constant, but duty cycle is variable. We assume ideal switch. The switch is ideal, so it switches on instantaneously and turns off instantaneously, and also there are no losses in them. So that is the assumption here. Initially ignore motor resistance. So we are going to ignore the motor resistance for this analysis. So usually when you compare the effect of the resistance, when you take a large motor, the resistance is usually small compared to the inductance. So we can choose to neglect the resistance, but depending on the the application, or you might include it. But for now, we are going to ignore it in the analysis. We also assume that the motor inertia is large, so the speeds and then the back EMF stay constant during the switching period. So the inertia is large. So we know torque and speed, back EMF and the speeds are related. So we are assuming that over the switching period is constant. So the speed doesn't change and then the back EMF too doesn't change. So the net change in current in the armature over the switching period, armature current over the switching period is also 0. So these are the assumptions we are making. So I hope that we all understand. So let's look at the choppers, the one quadrant chopper. So this is the one quadrant chopper, the diagram we have here. So this one is representing the motor. So its equivalent is it has a resistance, inductance, and then the back EMF that is represented by this one. So let's take note of that. This symbol represents the motor circuits, the back EMF, self-inductance, and also the resistance, because that represents the armature. I think we saw something like this, right? Something like this, where we have EB. So this is just a circuit that is represented by this one. I hope we get it. Okay, so now let's look at the properties of the one quadrant chopper. So before we analyze the operation. Okay, so the speed is in one direction, right? So we look at why the speed is in one direction. So we know that EB is equal to Km omega R. So whatever the value of EB is, if EB is negative, the speed will also be negative. But if it's positive, the speed will also be positive. So that means that the direction of the speed is determined by the EB value. But in this in the one quadrant chopper, the back EMF doesn't change. We also know that the VA is equal to EB plus IA RA plus L DI over dt. So we know this relationship. So we usually assume that this VA is almost the same as EB. So that means that if VA doesn't change its polarity, EB will not also change its polarity, right? So that means that the speed polarity will not change. So when we analyze the operation, we see why we are saying that the speed direction will not change. It's just forward direction. Then the torque is proportional to IA. So we have T to be equal to Km IA. So whatever value direction IA has, the torque to also have the same direction. So when we analyze the operation, realize that the current direction is just what? Forward, and it's positive. So because it's positive, the torque to will just be one, it will be in one direction, and it's also going to be positive. So speed is positive, torque is positive. So this will definitely be in the first quadrant. So when you look at the quadrant operation, let me just draw it in. So we have torque against speed. So this in this region, you have both torque and then the speed to be positive, right? And then here we have the torque to be negative and speed to be positive. When you come to the third quadrant, you have both speed and then torque to be negative. When you come to the fourth quadrant, you have the torque to be positive and speed to be negative. So we know that in the first quadrant, we have forward motoring, and in the second quadrant, it is forward regeneration. When you come to the third quadrant, it is reverse motoring. When you come to the fourth quadrant, it is reverse regeneration. That is from unit 1. This was what we learned. So we'll be making use of it, right? So because the torque is in one direction, speed is in one direction, and both are positive, this is going to operate in what? Quadrant 1. So this is one quadrant what? Drive. So let's look at okay. Let's look at this operation. Okay, so when you're doing we know that we are going to control the power converter by changing the duty cycle, right? So when Q1 is on, realize that it will be shorted. So power will be moving from the input through the armature, through the switch back to the supply. That's how the current will be moving. So that is the direction of the current. So let's say the supply current is IS, right? So IS will flow in this direction back to the supply. That will be the direction of the flow. So we also know that the machine, the armature, has self-inductance. So the self-inductance, because of that inductance, it will be storing up energy during the time that the Q1 is on, right? So it will be storing energy, and then some of the energy will be dissipated in the resistance. So you realize that VA will be equal to what? The average. VA here, we're looking at the average value of VA, which is, so VA is equal to duty cycle times what? VDC. So you realize that VA is going to be equal to what? VD. That is what will happen during the time that Q1 will be on. So we look at the waveforms, and then when Q1 is off, realize that the current is moving downwards, right? So when the switch is off, the diode is going to turn on, and there will be freewheeling happening. So current will still flow downwards, but it will be flowing in this direction. So it will be flowing in this direction. So you realize that the current direction is still the same. It's positive through at the armature. So we say that the torque is one direction, and then the speed to, since VA hasn't changed its direction, that means the EB direction will also remain the same. So the speed will not change its direction. So that is why you're saying that the speed is the speed is forward because it's positive, and then the torque to is in one direction because the current is in one direction, is in the positive direction. So this one will be doing motoring, because when you calculate the power, torque is positive, speed is positive. That means the power will be positive. So if the power is positive, it will be motoring, and because the speed is positive, it will be forward motoring. That is what we need to know. So let's look at the waveforms, right? So during the time that the switch is on, the current in the inductor, which is the current through the armature, because of the inductance, is going to be increasing. It will be storing up energy. So the current will increase from a minimum value up to a certain maximum. So when the switch is turned off, the energy that was stored in the inductor will now be released, and then the diodes will now be conducting. So during that time, the energy will be decreasing. So the current is going to what? Decrease until it hits a minimum, then the same pattern continues. And then the output voltage during the time that the switch is on will be equal to the supply voltage, that is VDC, right? So we have this to be equal to VDC. And during the time that the switch is off and then the diode is conducting, realize that if the diode is conducting, it's going to create a short circuit. So that means that it's going to short the whole of this from the supply. So the armature is no more connected to the supply, right? So this will be shorted out. So VA is going to be 0. So that is during the time that the switch is off and the diode is conducting. So that is why you see that it is 0 for this portion. Then the same pattern repeats. So when you focus on the supply current, when you come to the supply current, IS, when Q1 is on, current is flowing from the supply through the armature and back to the supply. So it will be equal to the current through the armature during the time that the switch will be on. But when Q is off, there is no, the current that is flowing is not going back to the supply. So during that time, IS will be 0. So when you come to the waveform, you will see that happening. So that is the time that the diode is conducting. So you realize that it's going to be off till the switch turns on again and the same pattern repeats. So that is what is going to happen, right? So from here, we can calculate the average value of what the output, that is VA. So what we do is we calculate, when you're calculating average, you get the total area divided by the period. So here the area is going to be VDC multiplied by T on divided by the period T. So this will be equal to the duty cycle times VDC. So VA average will be equal to that. So that will be the output DC. So this is what the load is going to see. Then you can equally calculate for the average what? Load current, IA. So this particular waveform, the average is given by the minimum current plus the maximum current divided by 2. So this gives us IA average. So that is what we are going to get. So this minimum and then the maximum here, you sum them and divide it by 2. So that is also given by that. So these waveforms, you see that the current is continuous, right? So this is for continuous. So for continuous, that is what we are going to have. So we look at the discontinuous case. So operation with continuous current, we know EB is the back EMF and it helps us to know the speed. IA is the mean current, which also gives us the mean torque. And VA bar is the mean armature current. And we are saying that the VA is proportional to what? EB. So when so the voltage control that we spoke about, by changing the input voltage, you're able to change the speed. That is what is happening. So, and you see that when we change the duty cycle, the output is going to change, right? So that means that we're able to change the speed. But that's how we control the speeds of the one quadrant chopper. So change in IA over a switching period. This is the change in the inductance current over a switching period, which is the same as the armature current, right? So this is what we need to know for the continuous current. So let's look at the discontinuous current. So the discontinuous current, during the time that the switch is on, it will current be flowing through the armature till it gets to a maximum So after the switch is turned off, it's the energy that was stored in the inductor will now be released. So let's say the current will be decreasing in the inductor, right? So when it decreases and it gets to zero, the energy that was stored is completely delivered by the inductor. There'll be no more current flowing. That is if during the time that the switch is off. So realize the current will be zero. We hit zero for some time before the switch turns on again and then the current starts flowing. So this is the discontinuous current we have, right? So realize that the current doesn't flow continuously over a switching period. It gets to the point that it hits zero. Then it stays on, it stays at zero till the switch turns on again. So this is not over a complete switching period. So that means that when you look at the output voltage VA during the time the switch is on, it will be equal to VDC. And then during the time that the diode is freewheeling, we'll have it to be zero. But when the current hits zero, you realize that VA will be equal to what? EB. So let's look at it. Let's go back and look at the operation that we had. So realize that this one is not conducting, right? So because this is not conducting, current is zero, the drop here is going to be zero. You will have VA to be equal to what? The back EMF EB. So that is what we are going to have. So during that time, it's going to be equal to what? The back EMF. So that is what we have here. So you realize that if you want to calculate the average of this waveform, it's not going to be the same as what? VA, average of VA equals to the duty cycle times VDC. So it's not going to be this. So it's going to be much complex, right? So we'll analyze the average current and then the average voltage. So let's take them one after the other. Okay, so if we ignore RA, realize that the average during the time that we have the continuous current, the average, the V EP is going to be equal to the average, right? So that is what we are saying here when you ignore RA, because we know that VA will be equal to EB plus VR, which is the one across the resistor plus what? VO. So since the average of since we are ignoring this, so that means that this goes to zero, and then the average of this one too is also zero. So you have the average of VA to be equal to what? EB. That is what we are going to have, right? So we know this expression already. So the speed to be equal to EB over KM. And then the torque two is also given by this relationship. But the average VA is no more equal to what? This. So we will not have this relationship for discontinuous current. Please, I hope we are following. So we need to now get a new average for discontinuous current. So let's look at the current. So the current to the average will also change, right? So let's look at the average. Because the current will hit zero, the change in the change will be the maximum minus what? Zero. So that will be the change in the inductance current. So in calculated average, we usually get the total area divided by the period. So when you look at over a switching period, this is the area we are looking at, this area. Right, so this is the area we are looking at. So we need to calculate for the average of this. So you can break it down into two. So if you break it down into two, right, into two. So we have this area and then the other area. So this area, because it's a triangle, so we are going to have the change in IA, right? Which change in IA multiplied by this, so this is what I'm saying. So change in IA multiplied by T on multiplied by half. That gives us the area for this part, and then the other side should be given by half times T2 multiplied by IA, change in IA. So this is what we are going to have. So this gives us the total area because this portion, the area is 0. So we need to divide the whole of this by what? T. So this will be the average current that we will have. So that is given by what? This expression that we are seeing here, right? So this is where it's coming from. Then we analyze the situation that the Q is on. So because we are neglecting RA, it will not appear in this what expression. So we are going to have VA during the time that the switch is on. We say that VA will be equal to VDC. So we are going to have VDC to be equal to EB plus LA times what the change in current divided by what? That's time that the switch is on. That is T on. So since we are neglecting the resistance, we will not have IARA. So from here, we can make IA, change in IA the subject. So if you make change in IA the subject, you are going to obtain this. So you can decide to bring EB to this side. So you are going to have VDC minus EB divided by LA multiplied by this. So that is what we are going to have. So we have this expression. And then during the time that the switch is off and the diode is on, we said that VA is 0. So you are going to have EB plus LA. Because the current is decreasing, the change is going to be negative. That is why we are seeing the negative sign here. So from here, we can also make T2 the subject. When you make T2 the subject, you're going to have VDC minus EB over EB multiplied by this one. So now we have T2 and we have change in IA, right? So we come and substitute these two equations into this one. So wherever we see change in IA, we are going to put as equation 2, and wherever we see T2, we are going to put equation 3. So when you do the substitution and you do the simplification, you arrive at this particular example. So you can try it yourself, or you just know that when you substitute them in, you're going to arrive at this. So the most important thing we need to know is we are supposed to know this one, know this one, know this one, and then know the other one. So when we know how to obtain them, then we can even do the substitution easily. So this will be the average current for the discontinuous average current. So we see that here the average current depends on EB, it depends on the duty cycle, right? So these are the two parameters that are changing. So duty cycle and the EB. So that means that if you want to change the average current, you either change EB or you change what? The duty cycle, right? So, and you can see that IA is no more proportional to what? The duty cycle, but rather the square of the duty cycle. All right, so let's look at what is here. So this equation is only valid for discontinuous current, which occurs at low torque. So this equation that we've obtained is just for discontinuous current. So if it is continuous, this equation will not hold, right? So we would usually set the duty cycle to be a constant value and expect the speed to remain roughly constant. So that is what we are going to do so that we can have the average current to be constant. So the duty cycle is going to be constant, and then we are expecting the speed to be constant, right? But when discontinuous current occurs, as IA goes down, EB increases for a fixed duty cycle. So let's look at the relationship. So if everything is constant, you realize that IA will be inversely proportional to EB. So if IA is decreased, EB2 will also increase. That is what is happening. So when you increase IA, EB will have to decrease because they're inversely what? Proportional. So that is what this statement is saying. So for a fixed duty cycle, right? That is what is going to happen. So when does the discontinuous current okay? So we want to know what happens so that we can even prevent it from happening in the first place. Because there is a tendency that it can happen in the 1 quadrant chopper. So how do we, so we want to know the time that it will happen so that we can prevent it from happening, right? Because we will analyze the impact of what the discontinuous currents on the output torque and then the speed. Okay, so let's look at that one. So we know that when we look at T2, T2 is given by what? Let's go back to the waveforms and then look at it. So when we come back to this waveform, this time is what? T on, right? So this is where we have T on. And then T2. So if the whole, let's say if the whole of this is T2, right? That is, we are looking at the portion that this is hitting 0 exactly at this point. So you see that the whole of this thing will represent T2. So that means that T2 will be equal to T on. That is the period minus what? T on. That is what is going to happen here. So that is when it just about like where discontinuous current starts from. So during that time, T2 is equal to T minus T on, and T on is delta T, right? And from here to we've calculated for T2, and T2 is given by what? This. So we can equate the two. So you're going to have VDC minus EB over EB multiplied by this to be equal to T minus delta T. So from here, we can do some simplification, right? So if we divide inside here by VA, you're going to have, sorry, EB, you're going to have DC over EB minus 1 to be equal to the other side. When we factor out T, so this should be multiplied by duty cycle T. We can also factor out T here. You're going to get 1 minus duty cycle. So realize that T cancels T. And when you multiply through by the duty cycle, you are going on this side, you're going to get duty cycle multiplied by VDC over EB minus duty cycle to be equal to 1 minus duty cycle. So you realize that this and that, when you bring it to this side, cancel this, and you're going to have duty cycle VDC over EB be equal to 1. So that is the point discontinuous current happens, right? So that means that if this value is bigger than 1, so let's say if we let's make duty cycle the subject. So we're going to have duty cycle to be equal to EB over VDC. So that is what we are going to happen. So anytime you have EB over VDC to be equal to the duty cycle, that is the point discontinuous current starts. So that is the threshold. But when you have EB over VDC to be more than the duty cycle, then we'll have discontinuous current. But if it is less than the duty cycle, we have continuous current. So that is what we need to know. And then the current is given by what? Duty cycle squared multiplied by T multiplied by VDC over 2LA into VDC over EB minus 1. So this is the average of what? The discontinuous current. So let's take note of this, and let's also take note of what? These two relationships so that we can know the time that discontinuous current occurs. So now let's now analyze the impact of discontinuous current. So we will look at it. But these were the, so let's look at some conclusions about the 1 quadrant chopper, both discontinuous and continuous. So in the continuous, we want it to be the chopper to act like a controlled voltage source where you control the output by controlling the duty cycle, right? So if you ignore the resistance, you are going to have this relationship. VA is going to be equal to EB. So from here, you can say that the speed is directly proportional to what? The duty cycle. And in this case, the speed is independent of the load. It doesn't depend on the output, the load that is connected. You can just change the speed by changing what the duty cycle. So that is ideally what we want. but the discontinuous current doesn't allow that. So these conditions are true if the armature current is continuous, but not true if the armature current is discontinuous. That is at low load torque. So let's look at the discontinuous situation. What happens? All right. So the discontinuous current, we will examine the torque speed characteristics for a DC motor fed from a one quadrant chopper in discontinuous mode. So we are saying that in discontinuous mode, we make the duty cycle fixed, so constant. We make it constant. Then we vary EB in order to vary the mean current. So you vary EB in the equation and see what value of IB will be, so that we can understand the relationship between the speed and the torque. Because EB tells us the speed and then IA tells us the torque. So that is why we are looking at these two parameters. And we also ensure that VDC is constant so that we can vary that particular term. So we know that IA average is given by duty cycle squared multiplied by T VDC over 2LA into VDC over EB minus 1. So we know, so we can actually vary this particular term. So that is what we are looking at, right? So if we start with the assumption that EB is equal to VDC, this corresponds to the base speed. So that is what we are looking at. So this will be equal to the base. So this term is represented with a constant called K. So K represents this term so that everything is constant. Then we just focus on the variation in this. Then we see what the average current will be. So that is what we are looking at. Okay. So we analyze a number of cases to understand what happens during discontinuous current. So the first case is when EB is equal to VDC. So when EB is equal to VDC, the ratio is going to be 1, right? So when we come back, so this is the expression we are using, K VDC over EB minus 1. So this is what we are looking at. So if this ratio is 1, that means that you're going to have 1 minus 1, which is 0. So IA will be 0. And torque 2 is given by KM IA. So if IA is 0, that means torque will be 0. So that is what will happen. And this is at the base what? Speed. So the machine is operating at the base speed. So if you look, let's look at the second case that EB over VDC is given by this expression 0.875, right? So that means that the speed that we are going to have will be equal to this times the base speed. So that will be the speed. But what is going to be IA? So we come back and substitute the this value. So IA average will be equal to K into, so this one will have 1 over 0.875 minus 1. So that is what we are going to have. And I believe if you simplify this this expression, 1 over this minus 1, you should come up with, you should get this expression. And then the torque 2 will also be this expression. So let's that is the second case. The third case, if we assume that EB over VDC is given by this, the speed will also be given by this. And when we substitute this expression, we get K into 1 over 0.75 minus 1. So when we simplify this expression, we get this. And when we substitute that into the torque equation, we also get this one. When you assume it to be 0.5, you are going to obtain this and that. So we can now plot a graph of the speed against torque for all the cases. So when we plot the graph, we are going to have the time, the ratio of EB against IE. So when we plot it, so you see that the time that the ratio is 1, the current was 0, and the EB and speed was what? Maximum, right? So we are going to have it, the first point here. When it's 0.875, when the ratio is 0.875, this is the IA we are going to get, right? So you plot it. So you look at each case and then you plot. I realize that as the ratio decreases, if we look at the current trend, the current is increasing gradually, right? And you realize as the speed 2 is decreasing and the current is increasing. So that is why we are going to have this, that's where this red one is coming from. And that happens during discontinuous current. So this is the load stock condition. During the continuous current, the speed is independent of what? The load. The speed is independent of the load. That is why you see that though the speed is changing, but the load is changing. That is IA is changing. Realize that the speed is constant. So that is what we need to know. So you see that during that time, the speed and the torque are not proportional. So let's look at what happened. So the droopy torque speed characteristics is bad. We don't want that to happen. So here, so we usually want a constant speed for a constant what? Duty cycle. That is, should not be dependent on the load. So we do not want massive speed variations for small change in what? Loads, for small change in load. So the characteristics can be improved. So because we don't want this, we are trying to look for ways of what? Improving the behavior during discontinuous caring, but we don't even want it at all. But if it does happen, we want to find ways of what? Improving it. So the first thing to do is to reduce the switching period. So when you reduce the switching period, we can what? Prevent discontinuous current, because when you switch, so if reduce the switching period also means that you also be switching at higher frequencies, because frequency is equal to 1 over T. If T is small, frequency is going to be high. So because you'll be switching at higher frequencies, the switching losses will be high. So it's not advisable, right? Or you can introduce extra inductance so that you can store more what energy during that time, so that the current doesn't fall to 0 before the switch turns on. So that is one way you can do that. So you increase the inductance to store more energy, right? But when you also do that, you are going to increase the size of the inductor that you are going to put, so that you can store more energy. And then the inductance will also comes with some losses, which will also be there. Another thing you can do is you measure the output and try to compensate for the difference, change in what? Speed. So you try to compensate for that. So you introduce a speed transducer and you add a control loop to compensate. But this one is an extra cost. So when you check the other, this one is expensive. So you can either choose this or choose the other one. Right? Please, any question on this? Any question on the 1 quadrant chopper? So the key takeaways is that, okay, somewhere are there you can talk.
I'm good.
You are fine.
Yeah, I'm good.
All right, all right. Okay. So that is what we will have. So what we need to know is that in the 1 quadrant chopper, discontinuous currents can occur. So we need to take note of that. So you can and it only does motoring. So we only have motoring there. Torque is positive, speed is positive, right? And during discontinuous during the discontinuous period, the speed is what it depends on the change in the load. So when you change the speed, when you change the load, the speed too will also change. So there are these variations that will happen. So we don't want this to happen. So we want to we want to be able to control the speed by controlling by changing the duty cycle. So we don't want that when the duty cycle is constant, the speed still changes with changing load. That is what we are saying here. So in summary, this one requires a small, simple hardware for the control, and the current can be continuous or discontinuous. So if the current is continuous, calculations are easier because we know that the output average is given by this expression, and the speed is independent of the load for a given switching, duty cycle. So if the duty cycle is constant, we don't expect the speed to be changing. We want the speed to be constant, irrespective of the load that is driving. If the current is discontinuous, this relationship does not hold. So for a given duty cycle, the speed is determined by the load. So if you want to improve the analysis, then you can introduce RA for the steady state calculations. So this is what we need to take note of, right? And then for the discontinuous current, let's take note of what the average current will be when discontinuous current occurs, and also the time that discontinuous current will occur. So let's take note of these values because it will be relevant in the analysis, right? And let's also take note of this for the continuous current. Please, exactly. Okay. So that is the one current chopper. So let's look at the two current chopper. So the two current chopper, let me zoom it out a little so that you can see the diagram clearly. Okay. So realize that in the one current chopper, we had Q1 and then D1, right? But in the two current chopper, we have introduced another switch and the diode. Look at the way they are connected. So we'll analyze the operation of this quadrant. So let's pay attention. When we understand this one and we go to the fourth quadrant, it becomes easier to understand that one. Okay, so I will spend some time here explaining the two quadrant chopper. So here, EB is positive because VA is positive. We'll look at why. When we're looking at the operation, realize that its polarity can never change. So because VA cannot change, its polarity does not change, EB2 will also remain. We'll have a constant polarity. That means that speed is going to be positive, right? Because VA is positive, speed will also be what? Positive because EB is positive. So that is why, so that is the first thing we need to take note of. But in this one, current can either be positive or negative. So when we are doing the analysis, we understand when current to be positive and when current to be negative. So because current can either be positive or negative, the top two can also be positive or what? Negative. So when we look at the torque speed, the four quadrants operation, realize that this portion this is when the torque is positive, right? And this is when it is negative. And the speed two is just positive, so it cannot be negative. So we'll be operating in quadrant 1 and then quadrant 2. So this is the two quadrant what? Chopper. So these are the two regions it will be operating. So we know that in this region, it is doing what? Motoring, right? But in this one, it is regenerating. Right. So that is what is happening here. So we will we will do the analysis and then understand how it is operating. So if you don't understand anything, please draw my attention so that I go over. Okay. So we understand why the current can either be positive or negative, and then the back EMF is positive. So let's start the analysis, right? So this is a principle of operation. So you see that we have two switches. They are switched on they alternatively, right? So they are switched on alternatively. So when Q1 is on, Q2 be off. When Q2 is on, Q1 be off. So that is what we are. That is how they are going to be operating. But we usually allow some distance, some time periods, so that the two are not on at the same time. When they both are on at the same time, we are going to have short circuit, so which will short the supply. All right, so we don't want that to happen. So we'll allow some distance, which is the lockout here. It represents some time that okay. So we usually employ fixed switching frequency, and we vary the duty cycle. So Q1 and Q2 are switched alternatively, right? So when one is on, the other one is off. So the two signals are complementary. So knockout is required because that is so usually a delay between the turn off of one device and then the turn off of another, so that we can prevent a short circuit from occurring. So when you're turning off one, you have to, when you're about turning on one, the other one should be off. All right, so you should allow some time, some delay, allow a delay so that both are not on at the same time. That is what we are trying to avoid. If both are off at the same time, then nothing is going to happen. But if both are on at the same time, short circuit will occur. So we want to avoid that. So that is the principle of operation. So now let's start the analysis. Okay. So the first thing we are looking at is when Q1 is on and Q2 is off, what will happen? So let's start. So when this is off, that means that this is opened, right? And Q1 is on. So when Q1 is on, it's conducting. So you have current flowing through the armature through Q1 back to the source. That is what will happen. So current flows from the supply to the armature, and energy is transferred from the source to the motor, to the load, right? To the motor and to the load, because we know that the load is coupled to the motor. So when energy gets to the motor, definitely the energy will be transferred to the load. Also, the armature inductance will also store energy in the form of a magnetic field. So it's going to store energy. Because of the resistance in the armature, there will also be heat generated. So some of the power will be lost in form of heat through the resistance. And then the inductance of the armature inductance will store energy. Will store energy. So this is what happens when Q1 is on, right? So VA represents the armature voltage, EB is back EMF, sorry, and IARA is the armature resistance. That is, this represents the armature resistance drop, and this is the armature inductance voltage drop. So you can write equations, right? Okay, so this is what happens. So this will be conducting, and current will flow from the supply to the armature back to the supply. So the armature has resistance, it has inductance, and then the load is also coupled to the shaft of the motor. So the armature, the inductance of the armature will store energy. The resistor will dissipate some of the energy from the supply, and then some will be transferred from the motor through the shaft to the load. So that is what will happen when Q1 is on and Q2 is off. So when you check the direction of the current, it's positive. It is flowing this way, right? So it's positive. So let me just draw the equivalent circuit of the armature. So we have this as, so this is our VA, and this current is what? IA. right? So that is what will happen. And this is our EV. And this is the inductance, and this is the resistance, LA. So IA is positive, so it should be flowing, like if you, it should be flowing downward, right? So that is what we are saying. So it should be flowing downward. So when you check here, you see that the current is flowing downward. So it is positive, right? So because current is positive, EB is also what? Positive in this case. So because EB is positive, current is positive, it's when you calculate the power, it's going to, speed is positive, torque will also be positive because the two are positive, right? So it will be motoring. So during this time, the drive motoring will be occurring. So let's look at the next operation. So something will happen here. So when Q2 is on and Q1 is off, what happens? So you realize that the inductor of the armature has stored some energy, right? So it will want to release that energy. So because it wants to release that energy, bear in mind, this is now on and this is off. So this is open circuit, right? So this is open circuit. Sorry, this is what will happen. So this is open circuit. So, but the inductor, the energy that's stored, it has to release that energy. So this is what happens. So because it wants to release that energy, its current, it will, we know that the inductor doesn't allow current direction to change. It doesn't allow the current direction to change. So it will want to keep the current direction in the same path. And it has to also release that energy. So because of that, D1 will turn on and it will turn on. So D1 will turn on and then the current that is stored in the inductance will be flowing. So current will be flowing in this direction. So realize that when you focus, when you come to the armature, you see that the current is moving downward, which is positive. So because it's moving downward and it's positive, this is what? Still motoring. Because EB is positive, the current is positive, right? And the diode is the one that is operating. So the stored energy from the armature inductance will be wasted as heat in the RA, and then some will be transferred to what? The load for useful work. That is what will happen. And that will continue because you realize that the motor is moving, right? So the motor is moving. So it still keeps the same direction of rotation. So as the energy stored in the inductor is decreasing, 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 definitely it will be used up. Right. So when it's used up and the current hits zero, what will happen is that when the current hits zero, the back EMF will force current to flow. So let's come here and look at it. So you realize that the energy here is zero, right? So current is no more flowing. So if current is not flowing, what happens? This back EMF will force current to flow. And bear in mind, the load is still rotating in the same direction. So it's still keeping the same direction of motion. It's not like the load is driving what? The motor. So it's going to act like a generator. So current is going to flow. The back EMF will force current to flow. So that means the current direction is going to change. So the current direction will change this way. So that is why we are saying that when when if the current hits zero, the motor back EMF forces negative current through what? Q2. Bear in mind, in this case, it is Q2 that is on, right? So it will force negative current through Q2. So Q2 will have to conduct. So when Q2 is conducting, you realize that the current has to flow down like this, right? So when you look at the motor side, it will be negative. So this is how the current will be flowing. That is um, the next operation. So when Q2 is on and then Q1 is off, this negative current will have to flow. So the negative current will be flowing in this direction, right? So when the negative current is flowing, it's not flowing to the source because there is no path to the source because Q1 is still off and there is no path to the source. So the energy will be transferred from the load to the motor, because it's now like the load is driving the motor. So energy will be transferred from the load to the motor, and some will be stored in the armature, and then some will be dissipated in the form of heat through its resistance, right? And you realize that the current that is flowing, the inductor will be storing energy again, though it's negative, but the inductor will be storing energy. So we say that the current magnitude will be increasing, right? Though it's negative, but the inductor is storing energy, so the current magnitude will be increasing. So we'll look at the waveforms and understand all of these things. So this should be the equivalent circuit we will have, right? So this time around, because the current has reversed its direction, but the back EMF direction has not changed. So that means the torque will be negative and speed will be positive. So when you calculate the power is going to be negative. So this is when it is what generating. So in this case, it is what regeneration is occurring. So during this period, regeneration is occurring, right? Okay. So if you turn off Q2 and turn on Q1, another thing will happen. So you realize that because the inductor is storing energy, right? It will not allow, and the current is negative. So it will not allow the current direction to change. Because Q1, so here Q1 is on. So it will not allow the current direction to change, right? So because of that, this D1 has to turn on so that the current, this was the direction of the current, right? So the current, this has to turn on so that the currents can find a path to flow, right? So because of that, D2 will turn on. So current flows from the motor to the supply through D2. So D2 will have to turn on, and then you have current flowing from the supply and from the motor to what? The supply. So energy is transferred from the load to the motor and to the supply. Also, the energy that was stored in the inductance of the armature will also be transferred to the supply, and its current magnitude will be decreasing because the inductor is releasing energy, so the current magnitude will be what? Decreasing. And some of the energy will also be lost in the armature resistance, right? So it will continue till the current magnitude. So if the current magnitude hits zero, because Q1 is on, the supply will force a positive current to flow. So positive current will be flowing, and then the operations continues, right? So during this time, you realize that the current is still negative, right? So it is still generating. So that's why we are saying that it operates in quadrant one and quadrant two. So it does motoring and then regeneration. So depending on which switch is on, and then the current that is flow, whether the current is positive or negative. So what I want you to understand is that know that what will happen, and then the current will be negative or the current will be positive. What happens when you turn on the switches? That is what I want you to understand. So if you have any question on this, please let me know. If you want me to go over, please let me know so that I can go over it again. Please, do we have questions? Or I should go over the
No.
explanation? Should I go over it? Okay.
Yes,
Since
because I didn't see the when you were drawing the line.
okay. So let's start again. We'll come to the waveforms, but let's understand the operation. So the first scenario we are looking at is when Q1 is on and Q2 is off, because they are switched on alternatively. So when one is on, the other one is off, right? So both cannot be on at the same time. So when Q1 is on, Q2 will be off. So you see that Q2 is off, Q1 is on. So current will this will be shorted, right? So current will be flowing in this direction. So that is the direction of the current flow. When you look at it, it is positive current that is flowing. And EB is also what? Positive, right? So because EB is positive, current is positive, speed will be positive, torque will be positive. So the power will also be positive. So it will be motoring. So that is what will happen. So current will flow from the supply to the armature. And because current is flowing through the armature has inductance. So that inductance will be storing energy as well. And then the armature too also has resistance. So heat will also be generated as a result. So energy is transferred from the supply to the motor and to the load, and also to the armature inductance. So it will store energy, and then the armature resistance will waste some of the energy in the form of heat. So that will happen. That is what will happen when Q1 is on and Q2 is off, right? So that is, let's say, when you start the motor with Q1 on, Q2 off. So the motor is started and is operating. So when you turn off Q2 and turn on Q1, this is what will happen. So you know that the current is flowing in a certain direction, right? It's positive. The inductor doesn't allow currents to change instantaneously and do not allow the current direction to change. So because of that, it will so keep the positive current direction. So for the current to continue to flow, let me erase. Okay. So for the current to continue to flow, we need to find a path that will allow positive current to flow, right? So that is what I want us to know. Okay. So for the current to be positive, right, it's flowing downward. So what should happen? Q2 is on, but Q1 is off. So because Q1 is off, there is no path for it to flow. This is open circuit. So positive current cannot flow here. The diode 2 doesn't allow current to flow in what? It allows current to flow in one direction, right? So the diode, this D2 will not allow current to flow in this direction. So Q2, though it's on, the current needs to flow like this, right? It will not also allow current to flow. So the only one that will allow current, that positive current to flow, is what? D1. So D1 will allow the current to flow. So that positive current will be flowing like this. So that is why we are saying that the current is positive. So when the current finds a path to flow, the inductor will be releasing the energy that was stored. So it will be releasing the energy. So that energy will be going to the load for useful work, because the load is still coupled to the motor, to the shaft. So some of that energy will go to the load, and then some will be wasted as heat. Please,
You can't see.
you can't see.
Yeah, there's nothing showing.
Okay, I'm coming. Let me reshare my screen. Okay, please, is it showing now?
No, please.
My own is showing.
I think you have to check your internet connection. So, can I continue?
Yes, please.
Okay. So we understand why the D1 will conduct, right? Okay. So the energy that was stored in the armature inductance will now be released. So some will go to the motor and some will be dissipated as heat in the armature resistance. So if, during this time, realize that the is disconnected from the source. So no current is coming from the source, right? So if you allow it to operate, if you allow it to operate, realize that the current will go. The energy that was stored in the inductor will keep reducing till all the energy is released. So when that happens, current is going to be zero. So yeah, it's from this relationship. This is the energy stored in an inductor. Right. So if energy is zero, that means that current will also be zero. So when it releases all the energy that was stored, the current will be zero. So that's what will happen for the current to be zero. So if the current reduces to zero, when the current gets to zero, realize that the motor back EMF is still there. So the motor back EMF will force current to flow. And when that current is flowing, it will flow in the opposite direction. So that is what I was showing us here. So it will now be acting like a generator. So now current is zero and it's not connected to the supply again. So the back EMF will force current to flow. So the current will change its direction. So when it changes its direction, it becomes negative. So that is what will happen. So current will now be flowing it will now be flowing in that direction. Right. So that is what will happen, and then negative current to flow. Right. So when we have the negative current flowing, I'll come back to these waveforms. So let's finish here. So when you turn on Q2 and then turn off Q1, right? So we understand the condition for the negative current, right? So when we now turn off Q2, turn on Q2 and turn off Q1, realize this is off and then this one is on, right? So when this one is on, that negative current, the negative current that is flowing will need a path to flow, right? So it will be flowing through Q2. So it will be flowing through Q2. And when you check the direction, it is opposite to the original flow. So that's why we are saying it's negative. So it will be flowing through Q2, but still during this time, it is disconnected from what? The supply. Nothing is going to the supply. So the energy is transferred from the load. It's not like the load is driving the motor. So energy will be transferred from the load to the motor. And some will also be stored in the armature resistance and some will be dissipated. So you realize that with time, the inductor will keep storing, its energy will keep increasing. So when you check the magnitude of the current magnitude will be increasing, right? So that is what we need to do. So this is the equivalent circuit we are going to have. So that is what will happen when the negative current is flowing. So when we turn off Q2 and we turn on Q1 again, that negative current, the inductor will not allow the direction to change. So it still wants to keep that negative current. So that negative current needs a path to flow. So now Q2 is off. So there is no path here. Q1 is on. So, but the current direction is already upward. So it's Q1 will not allow the current to flow. So that means that the only path for the current to flow is through D2. So D2 will allow the current to flow to the supply. And when you look at it, current will be flowing in this direction to the supply. So this is during this time, the motor is connected back to the supply, right? So the energy will now be moving from the load to the motor and then to the supply, right? Because during this time is the load that is driving the motor. So it's generating. So some of the energy that was stored in the inductor during this period will also be released. So it will also be released. That is what will happen here. So it will also be released. So you realize that when the energy is released, when the inductor keep releasing energy, it decreases, and then the current too also decreases till a point that hits zero. So when it hits zero, and then when it hits zero, the supply will now force current to flow because this is still on, right? This is still on. So the supply will force positive current to flow. So when positive current is flowing, it will flow through this, not this, and this will be off. This will be off. This is off. So current will flow through this, and then the same thing repeats. So that is how it operates, right? So we can look at the waveforms. So when you look at this waveform, this is for the motoring when it was motoring. So we are looking at D1 and D2. So this is what you are going to have. So when it's motoring, this is the current that will flow. When you just focus on motoring, I think we are familiar with this waveform, right? So that is when Q1 is on. When Q1 is on, you see that the current will be rising. Then when it's off, it decreases. But during that time, Q2 is on. So that is what will happen. So we just focus on the monetary aspect. So this is what we're going to have. The supply current will be positive. But during the time that is generating, anytime Q2 is on, we are going to have the current to be negative, right? So we'll look at it. This is actually in the negative region. So this is a zero line. Let's take this is a zero line. So it's actually in the negative region. So, but the other one was in a positive region. But this in the generation, when it's generating, the current is negative. So it is in the negative region. So this is the waveform we will get. So when we put all the waveforms together, we'll arrive at this. So this will be the motor current. So this will be the motor current. So you realize that in this form, we don't have any discontinuity. So either the current is positive or it's negative. So we don't have any discontinuity. So in a two current chopper, the current is always continuous. So you might want to also focus on the output current. The VA. When you look at VA, anytime when D2 is conducting, it connects back to the supply, right? So VA will be equal to what? The supply voltage. When Q1 is conducting, it's connected to the supply. But when Q2 is conducting, it is disconnected. When D1 is conducting, it is disconnected. So that is why when you look at this waveform, anytime D2 is conducting, VA is equal to the supply. When Q1 is conducting, it's equal to the supply. But when D1 is conducting, it is disconnected. When Q2 is conducting, it is disconnected. So that is the waveform you are going to get. So you can actually look at it and then you calculate for the average and realize that the average will be this for all operating conditions. Please, any question? So this is like this waveform I see is for a series of operations. So it's for a series of operations. So let's say if we want to understand it well, let's start from here. Let's start from here. When Q1 is on, realize that the current will be increasing, then it hits a maximum. So when D1 is conducting, it will decrease until it hits zero. When it hits zero and Q2 is conducting, that time the current becomes negative. So this time you see that the magnitude is actually increasing, right? But the current is negative. So that is when Q2 is conducting. So it hits a maximum when G2 is conducting, the magnitude will be decreasing to zero, then Q1 takes over. That is what happens. So you have series of this and waveform occurring. So that is what happens. Please, I hope you are fine. We understand the waveforms, we understand the operation, right? Okay. So during the interval, during the on time, right, that is delta T, the supply is connected to the armature either through Q1 or D2. We've seen that, all right? And during this interval, the armature is shorted either through D1 or Q2. We've seen that. So this is always positive, right? Because this is always positive, EB will always be positive, right? So if EB is positive, that means that speed will be positive. But IA is given by what? This, the average is given by this. So realize that there are sometimes that this is actually VA. There are sometimes that VA is 0. So anytime VA is 0, you see that the current is negative. But when VA is equal to this, then you will have the current to be positive. So anytime current is positive, it's motoring. When current is negative, it's regenerating. So this is a summary of the two-quadrant chopper. So let's look at the conclusions. So two-quadrant chopper behaves like an ideal control voltage source because you can control the output by controlling the duty cycle. And the controlled voltage is usually positive. So armature current, that's the torque, can either be positive or negative, right? And this continuous current doesn't exist. So current is always continuous. So in this the two-quadrant chopper, we don't have this continuous current. So we will not encounter the drooping torque speed characteristics. So speed is determined by duty cycle alone and is independent of the torque, except for slight changes due to the resistance in the voltage drop. You realize that when we are doing the analysis, we are not focusing on the drop in resistance, right? Then we neglected the resistance, but when you include it, there might be some slight changes because during steady state operation, we know that VA is EB plus IA RA. That is steady state. So we realize that this might make VA not to be equal to EB, right? So that's what he's trying to say here. So that is the two-quadrant chopper. So when you understand the two-quadrant chopper, we can do the connection in another way to get another two-quadrant chopper. So when we put them together, then we have a four-quadrant chopper. So for the four-quadrant chopper, this is the diagram. When you look at it carefully, you can see two quadrants, and then you can see two quadrants, and then you can also see four quadrants. So this one, it has a lot of ways, a lot of different modulation strategies, but the easiest one is what we will look at. So you can control it in a lot of ways, but the easiest one is what we will look at, which is here. So I'll come back to the diagram, but let's look at how it is controlled. So when you want to do one quadrant and two quadrant control, what you do is you keep Q2 permanently on and Q1 permanently off. And then you can control the chopper, the two quadrant chopper, by controlling the Q1 or Q3 or Q4. Right. So you can do that. So during that time, the speed is forward. And you can, so that is what will happen. So let's come back here. So what he's saying is that we should keep this one should be off permanently during the two quadrant 1, quadrant 2 operation, and this should be permanently on. So that means that here we'll have open circuits, right? So, and this is short circuit. So we can either control it by controlling this or controlling that. That is what he's saying. So let's just look at the situation that Q3 is on. So let's just say for starting, Q3 is on. Realize the current will flow like this. Show this one. Like this back to the supply, right? So you can have something like that. And let's say, let's just make, because there are a lot of things you can look at. So I just want to explain some scenarios. So let's say if this is off and this is on, right? If this is off and this is on, the only part for the current to flow is what? This has to flow downwards. That means the current will have to flow like this, through this one like this. So that is, you take, when you are, but if you understand the two quadrant chopper, you can take your time, look at the scenarios, analyze them one by one, and you will understand what will happen, how it's going to be controlled. And if you want quadrant 3, quadrant 4 operation, you permanently on Q1 and permanently off Q2, and you can control the operation by controlling Q3 and Q4, right? But you know that during that time, the negative becomes the voltage becomes negative, and then the speed is negative. So that is what will happen. So when this is permanently on, realize that current will want to flow like this, which is in the negative direction, right? But this is in the negative direction. So this is going to be negative. Because when you want to take a lobe like this, realize that you have VDC to be equal to negative VA. So VA is negative. So EB will be negative, current will be negative. So this one you can do the analysis and you have all four quadrants. So that is it. So simply as it is. So any question before we take examples? Okay. So let's look at the examples. So this example says a DC motor has a rated values of 230 volts, 500 RPM, 90 amps, RA is 0.115 ohms, LA 0.011 Henry. A two-quadrant chopper uses a supply voltage of 230 volts and has a switching frequency of 400 hertz. The first question says, calculate the speed for motoring at half the rated torque when duty cycle is equal to 0.5. And the second one says, we should calculate the speed at duty cycle equals to 0.5 when generating at rated torque. Okay, so these are the motor parameters, and this is the power converter parameters. Okay, so we are interested in calculating speeds, right? So now, speed omega R is equal to EB over Km. So we need EB, we need Km. So we have to look at how do we get EB, how do we get Km, right? So EB, we know VA is equal to EB plus IA RA. So when you look at this expression, VA, we know VA already because we've been given the duty. VA is given by delta VDC. VDC, this is the input to the chopper. So this is VDC. VDC is 230 volt and duty cycle is 0.5. So we know VA. IA is given in the question. IA is given, which is the rated. But since we have been told that at half the rated torque, we know that TE is equal to Km IA. So we've been given rated current. Rated current gives us rated torque. If you're looking at half the rated torque, that means IA should also be half, right? So IA will be half of what the rated, which will be 45. RA is given. So the only unknown is what EB. So from here, we can calculate for EB, right? So you write the equation, if you make EB the subject, you're going to have VA minus IA RA. You know VA to be 230 times 0.5 minus 45 times what? This value. That gives us EB. So from here, we know EB. The next thing we need is what? Km. Km is so Km, we usually operate the motor at the rated flux. So because of that, we need to use rated values to get Km, right? So we come and look at the rated values of the motor. We've been given speeds, right? So we will still use the same equation because we know the rated voltage, input voltage, which is 230. We know the rated speed. So that means that we can so we come here. We know EB is Km omega R. So wherever we see EB, we can put this there. We know our R, we know IA. So the only unknown here is what? Km. So you make Km the subject and you substitute in the values to get it. Then you come and put it here. Use your new EB that we calculated at half the rated torque with Km to get the speed. That is how you go about solving the first example. So we will go through it. And the second one, we are told that the speed at what when it's generating, right? So bear in mind, this is still the input. This is the input to the power converter. So that means that we can calculate our VA. VA will still be equal to 0.5 times what this. But now it's generating. So when it's generating, current is usually negative. So you come and use, but we are told it's rated torque, and this is the rated current. Rated current gives us rated torque. So we pick the rated current and make it negative. So EB will be equal to VA minus what? IA RA, because it's now generating. So this becomes minus. So you calculate for EB with our Km value, we can get speed. So let's go through it. So these are the motor parameters that we are given, right? So these are the chopper parameters. So the first, we are looking at this. So let's go through it. So when you write this will be the armature equation, but we know that during steady state, this is 0. So we'll have this to be equal to this plus this, right? We know VA to be equal to this one. So you make EB the subject. When you make EB the subject, you're going to have VA minus IARA. You do the substitution. So we understand where this 45 is coming from, because it's half what the rated torque. So this is our EB. So we need to get Km. So in order to get Km, okay, here he's trying to use some he's using some proportion. So let's look at it. So he's calculating the EB at rated. So when you calculate EB at rated, you are using the same formula, right? So we need to use rated values. So that's why this is 230 and the current is 90. So you're going to get this. So EB at the rated speed is this, right? So you have 219.65, which is proportional to what? 500. So if you have 19.83, what will it be? So because the EB, this is from EB equals to Km omega R. This is a constant, so we can just say that this is proportional to that. So from that proportionality, you can obtain what your new speed. That is what you can do. Or you calculate for Km and you come and substitute. So that is what he did here. So he used the proportionality to get the speed in RPM. Any question on the first one? Okay. So the second one, because it's generating, IA will be negative. So we do the substitution, and so the output VA will be 0.5 multiplied by 230 minus, because IA is negative, it's generating is negative, so you just put it. Then you can get EB. And with the same proportionality, you can obtain the new speed, or you calculate for Km and then do the substitution. So that is how you go about solving this example. Any question? Okay, so if there is no question, then we look at other examples. So this example is on 1 quadrant chopper. So a single quadrant chopper fits a DC machine, which has the following parameters: RA to be 0.2, LA to be 10 millihenry, Km is 2 volts seconds per rad. The chopper supply voltage is 400 volt. At a particular operating point, the speed is 100 RPM, and the mechanical output is 8.4 kilowatt. The peak-to-peak armature current ripple at this operating point is 10 amps. The first question says we should determine the duty cycle. B, the approximate switching frequency, ignoring the effect of RA. And C, the power loss in RA, assuming that RA is constant regardless of the frequency, and making suitable simplifying assumptions about the armature current waveform. So now, the first is the duty cycle, right? So the duties, so we've been given what? The output power. We've been given the speed. So we have a number of information. So how do we go about it? We are interested in duty cycle. So we know that VA is equal to the duty cycle times what? VDC. So if you're able to get VA, then we can get our duty cycle because we know what the supply input voltage. So that should be our target. So now, let's use what we have. So you see that we have this as the output, right? And output is given by T omega R. So from here, this is P naught. So from here, you can calculate for TE, right? Or you can even calculate for EB. So what we are trying to do is you want to get EB, you want to get IA. Because when we get IA, VA is given by EB plus IA, RA. RA, we know RA. We need EB and we need IA to get VA. So from here, we can KM is given already, so we can get EB. So EB be equal to KM, which is 2 times the speed, right? So that will be 2 times 10, and that is 1,000 times 2 pi over 60. So this gives us EB. So the next, what we need is what? IA. So in order to get IA, we can use this expression, right? Calculate for TE, we know K, and we can get IA. Or you can use the output. Okay, here we've not been given anything concerning efficiency, so we are limited to just using this one. So from here, we can calculate for TE. TE is what? P naught over omega R. So P naught is given by this, that is 1.8 times 10 to the power minus 3 divided by the speed. So you multiply this by 2 pi over 6 to get TE. So when you get TE, we know K and we can get IA. Then we substitute it here to get VA. Then we come to this one and then get what? Our duty cycle. Please, do we understand? Like, please, do we understand? So, okay, personally, this is what I do. So I usually look at what am I looking for? I write the relationships down. What information do I have? What do I need to calculate? That is what I usually use to help me solve these examples. So if to also help you, then you can also adopt it. So write your equations down. Look for the parameter you're looking for. What do you need to get that parameter? What information is available? That is how you can go about it. Okay, so we understand how to get our duty cycle. So the next is to get what? The switching frequency, right? So this is to get a switching frequency. Okay, so we are interested in getting the switching frequency. So we've been giving the peak-to-peak ripple, and so we are asked to neglect RA. So we are asked to neglect RA. So we need to get, okay, the information that is given here. This is what we are giving. This is what we are giving. And we need to get the switching frequency. So this is what we do. So you remember we're given a formula like I change in IL is equal to, I think, VTA over L. Do you remember any formula like this? Please, do we remember? Because that is what we need here. So the reason why we are doing that is we know that duty cycle is equal to T on over the switching period. So we know the duty cycle. So when we know T on, then we can get what? The duty, we can get a period. So to help us get the T on, we use this particular one. So this is the voltage time area over the inductance. So inductance is known, this is known. The voltage time area. So because we are ignoring RA, right? Because we are ignoring RA, VA is going to be equal to EB. So VA will be equal to EB. So if we ignore this one, so you just have VA, sorry, it will be equal to the supply. It will be equal to, so we have to draw the waveform. So the waveform we saw, so we are just focusing on the one across the inductor. So this is what I'm saying. EB plus VL times IA RA. So we have to neglect this. So that means that this one VL will be equal to what? VA minus EB. So that is what we are going to use, right? So that means that during that time, the VL is going to be like this during the on time. But when it's off, we know VA is going to be 0. So VA will be 0. So it will go into the negative region. So this is T on and then T off. So what is this magnitude? So when you look at it, is VA minus what? EB from here. So we need to get the EB at this operating time, during this operating time. So EB, because, okay, so this is what we need to know. So when we calculate the average of this VA, this one goes to 0. So you realize that EB will actually be equal to the average, right? So this will be equal to the average. And then VA, during the time that the switch is on, VA is equal to what? VDC. So this is going to be VDC minus VA average, which is basically, that is what we are going to have. So this is the area we are going to use, right? So the VTA will be equal to VDC minus VA average times T on. So that is what we will get. So T on, so from here we can obtain T on, right? So we come back to this relationship and then make T on the subject. So when you make T on the subject, you're going to get T on to be equal to change in I a multiply by inductance divided by what? VDC minus VA average. So all this information is known. So we do the substitution, get our T on. So when we get our T on, T will be equal to T on over duty cycle. Then that helps us get our switching one period. So when we get the switching period, obtaining the switching frequency becomes easier. Any question? Should I go over? Or maybe when we are going through the solution itself, we will understand what is happening. So that is how you go about solving the B part of the question, actually. Then the C, you have to calculate the power loss. So we need to get the average current that is flowing. Sorry, the RMS current, actually. So we need to get the RMS current, square it, and multiply by the resistance. So that is what we are going to do. So we know how to go about it. So let's take let's look at A and then we continue. So this is the output power. This is the speed. If you convert it to RPM, sorry, rad per second, you're going to get this. So to get the output torque is equal to the output power divided by what? The speed. So this gives us our output torque. So we can use that to calculate what the current. So we know TE is equal to KMIA. So you make IA the subject, which will give you this expression. And when we substitute the torque into this expression, you get IA to be this, right? Now we have IA, right? So the assumption is that this is very, the average is larger compared to the ripple. So we say that the current is going to be continuous, because look, when you look at it, so when you draw the waveform, why we are saying it to be continuous is that the waveform, it looks like this, right? And then this change is IA, is the difference between the maximum and the minimum. That is what we are going to have. So if you want to know, so the average is actually 40. So if between this maximum and the minimum is 10, that means that the lower value will be what? 40 plus 40.1 minus 5. And then the upper one will be 40.1 plus 5. So you realize that this minimum is not 0. So it's above 0. So that's what we are saying is continuous. So this is how you're able to check whether it's continuous or discontinuous, right? So because it's continuous, we can proceed and calculate for the VA. So the VA, we know how to obtain VA, right? So we get EB, get IARA. So we know IA already. EB, we've calculated for EB already, right? So from here, we know EB. So we substitute to get VA. Then we use this one, right? I hope we get it. Please, do we get it? Okay. I think we get it. So the B part, the B part, we are saying that we want to calculate for the switching period, a frequency rather. So here, and a different approach is used, but that is the same thing I was doing. So we know that during so we are asked to neglect, but this is a formula we have, right? So this is what we have. So we are asked to neglect this. So you are going to have this to be equal to EB plus this. So that is what will happen. So this will be the voltage across what the inductor. So which is equal to the, if you make some approach, this which, so that's what will happen. So during this time, during the time that the switch is on, we are saying that VA is equal to VDC. That is why you are seeing that VA is replaced by VDC, right? Then you will get which will be equal to this. So you can make T on the subject. So you can do the substitution. So realize that the EB is the same as what the EB that was obtained here. Please, do you get it? The EB is the EB that was obtained here. So because we neglected IARA, this is neglected, right? So it will just be left with EB. So we can do the calculation. So that is what will happen. So you use this one, then we know the change in current already. And this is the inductance. So you make T on the subject, and then you are going to obtain this and use that to get the period. So when you get the period, then you can calculate for the switching mode losses. Please, I hope we understand that. Then we can calculate for the power loss. Any question on this example? Okay. So if there is no question, then you can look at the next example. A tram is driven by 1,500 RPM, 60 volt series connected DC motor with a full load current of 200 amps. The combined field and then the armature resistance is 0.1 ohms. The supply voltage is 700 volts DC, and the chopper frequencies varies between 50 and 1,600 Hz. But the on time remains constant at 600 microseconds. So we should calculate the chopper frequency and then the supply current drawn when the motor is at standstill, noting that the motor current is limited to 240. And the B says we should calculate the switching frequency and the supply current drawn at the rated output. So let's look at it. So we are looking at the switching frequency. Yeah, this is constant. So this one is constant, irrespective of the switching frequency. This is constant, right? We've been told that it's a series motor. So the choppers, we are looking at the chopper switching frequency and then RA at standstill. So at standstill, what happens? EB is 0 at standstill. So because EB is 0 at standstill, we can use that information to get the so we can get our VA during that time. So when we get VA during that time, then we can get a switching period. Then we can get we can get the duty cycle. Then we get the switching period, and that will help us get the switching frequency. And we can use that to get the current. So the motor current is limited to this, right? So as so we know that, okay, let's write the formula. VA is equal to EB plus IA RA plus LA GI DT. So at standstill, this is 0, right? And we are also looking at steady state operation. So this is also 0. So VA will be equal to IA RA. So from here, if the current is limited to this, then we know VA already. So VA will be equal to 240 multiplied by 0.1. And we can, and this is the input. So we can use this to get the duty cycle. So when we get the duty cycle, then we can come and we know this is constant. So the T will be equal to T on over duty cycle. So from here, we can obtain the duty cycle and then come and substitute it to get to the period, and that will help us get the switching frequency, right? So that will be okay, let me see. So that you're asking for supply current drawn when the motor is at standstill. Okay, I'm coming. I think it should be equal to the rated rather. So they're asking for the supply current again. Let me check. This is equal to this. EE. I think so. That is if I think VA should be equal to the supply rather. The supply voltage should be equal to the supply voltage, which is this one. So I think that what I've done will be wrong. So we use this one, VA, we know VA to be this. Then we can now use this one to get IA, right? So by dividing this by the RA, I think so. So this is a series, I think it should be this. And this is the applied voltage. So you see it's EB is 0. Okay. Okay, I think that's how we should go about it. So that is how we should go about it. And then we can calculate for the current drawn when the motor is at standstill. So see, maybe I'm missing out on something. Okay, maybe this might have some drop. Maybe it might not be zero. Maybe that's what I'm missing out on. So with this current, we can actually get this value. I'm not sure about that. That is what I'm thinking. If you can get this value, I don't know whether it will be zero or not. Because if we assume that this is the voltage that is applied, realize that the current should be far above what this one. So okay, let's go through the solution and then see what will happen. Okay. So the duty cycle, since this is zero, we are going to have VA to be this, then this gives us the duty cycle, and then we can use the duty cycle with the on time to get the switching frequency. So this is the switching frequency. All right, so the current that is there, okay, it was obtained using the power loss equation. So if you assume that the power loss in the converter is zero, okay. Sorry, what I was missing out was I was confusing the motor current with the supplies current. Sorry about that. I was confusing the supply current with the motor current. That was the issue. So this is the motor current, and we are looking for the supplies current. So it will be different, right? Okay. So we have to use the assumption that the power loss in the converter is zero. So whatever power that is coming from the supply will be equal to the output. So now we know the we know IE, we know VA. So this will be at the output. And then this one is the input. So the input of to the power converter will be the VDC times the input current of what? The supply. So when we make I in the subject, then we know this is 700. This is not known. This one we just calculated is 24. This is 240. So we make I in the subject. So if you make I in the subject, you are going to get P out over VDC. So what should be VA average over multiplied by IA divided by VDC. So we substitute in the values. So this is 24. And then the other one is the IA is 240 amps. This is VDC is 700. So we substitute it and that will give you the supply current. Please, do we understand? Then when we are calculating for this one, we need to do the same thing. So we need to get our VA. So when you get our VA, then we'll get the switching frequency and we can also get the rated. So this one is at the rated supply. So the rated supply, you know that this will be there, right? The rated current, so this will be there. So EB will be there. And then we'll have IARA to help us get VA rather. So we need to get the EB as rated. So EB as rated, we know that we have 600. I think if it's at rated output, I'm expecting it to be 600. So I don't think this one, we need to do it. We don't need to do any calculation, right? But we're expecting that the output should be 600. So that is it. So we will have 600 over 700. And then with that, we can get we go through the same formula, use the same procedure. So here, because it's at the output, VA will be 600, IA will be 200. Then we calculate for the switching frequency. This is the duty cycle. And we get the switching frequency. Then with the same approach, input power is equal to output power. Then we substitute in the values to get IE. So that is how you go about this. Let me see how many more do we have. Okay, we have one more, and it's 7. Okay, should we continue with this example? I think this example is on discontinuous current. Should we do it or we should
Yes,
leave
we should
it?
do it.
Okay. So a single quadrant chopper feeds a DC machine with an armature inductance of 5 millihenry and a motor constance of 2.5 second per rack. The armature resistance may be neglected. The chopper is fed from a 400-volt DC supply with a switching frequency of 1 kilohertz. Stating any assumptions made, determine the speed of the armature if the duty cycle is 50% and the load torque is 100 Newton meter. The second one says the torque is now reduced to 20 Newton meter and the duty cycle is maintained at 50%. Verify that the armature current is discontinuous and calculate the new motor speed. For the condition in II, determine the duty cycle required to bring the motor back to the calculated value in I. Okay, so the first, we are looking at the motor speed, right? So we've been given torque, we've been given duty cycle, so we can calculate VA. So VA will be 0.5 times what, 400. So that is VA. From this one, we can calculate for IA, right? So we can calculate for IA. IA will be equal to 100 over km. So km is 2.5. So I'm expecting 40 or so. So this one will give us 40, I think. So you have 40 amps. So with this, we can calculate for EB, right? So EB be equal to, this is 200 minus 40 times what? I'm coming. Okay, we've asked to neglect the armature resistance. So if we neglect the armature resistance, then VA will just be equal to what? EB, right? I think that's it. So VA will be equal to EB. So we don't even need to do any calculation. So we know EB to be equal to 200. So if EB is 200, then we can calculate for the speed. So the speed will be EB over KM. So you have 200 over 2.5. So this will be 80 rads per second. So you can convert it to RPM. So RPM 80 by 60 divided by 2.5. So that is how we go about the first one. And the second one, you're told that the torque is now reduced to 20 Newton meter, and then the duty cycle is maintained at 50%. Verify that the current is continuous or discontinuous. So we should verify that it's discontinuous. So what we need to do is we need to first of all calculate for the IA, right? So the IA will be equal to 20 over 2.5. That is what we do. So this gives us I think the 8 amps. So we are going to get 8 amps. So this will be IA average. I'm talking about the average, right? So this is the current we are going to have. How do we verify whether it is discontinuous or continuous? So this is where we have to now go back to the formula that was given. So the formula that we saw, so that IA average during the discontinuous current is equal to duty cycle squared, the period times VDC over 2LA into VDC minus E. EB minus 1, right? So this is what we are going to do. And we know that the duty cycle T2 is equal to what? VDC. Sorry, I think VDC minus EB over EB times duty cycle. Okay, all right. Let me write it here. T2 was giving us VDC minus EB over EB times. So we saw this, and we saw another formula. T2 was T minus duty cycle times P. We also saw that this is at the point of discontinuity. So with this, it can help us get, we know the switching frequency, we know our duty cycle, so we can do the calculation and compare to see what we are going to get. So first of all, we need to be able to do this calculation. We need to get VDC over EB. So we can do the substitution here. So we can do the substitution here to get this thing, right? So we know IA to be 8 amps. This is given. Switching period is given because we have switching frequency. VDC is giving us 400. Inductance is giving us 5 millihenry. So we can do the substitution in this expression. Then we get this one. So when we get this one, then we come back and do the substitution here. So we get T2. So when we get T2, we now come and check. When we take T minus duty cycle, we'll compare the two values. So we'll use this one and then that one to compare the two values to see what it will be. So that is how we go about this one. So when we get that one, then we know how to get a new speed. Then we'll come back here and then. So when we verify that, then we'll come back here and calculate for new EB, and that gives us with KM, we can get the new speed. And the last one, they are saying that we should determine the duty cycle required to bring the motor back to the same value. So we know the speed already, right? So if we know the speed that was obtained here, what duty cycle should we use so that the speed will be the same as the one here? So what we need to do is we definitely use this one because we are experiencing discontinuity. So we have to find this one. We know the speed already from here. So we know the EB from here. So we just substitute it here, calculate for the new duty cycle, and that is how we go. That will be the end. So let's go through it one by one. So we are starting with the assumption that it is continuous. So that is what the assumption we are starting with. So for the first one, so we can do the calculation and check. So if we neglect IA, VA will be equal to EB, right? So we calculate this was VA. VA will be duty cycle multiplied by what? VDC. So which is 20. So which will be equal to EB. So with this one, we can get what? Omega R. So 200 divided by 2.5. We get 80 rats per second. So you convert it to RPM. So this is what you're going to get. So this one, because we have to check whether it is discontinuous or not, we will start with we will start by saying that it is discontinuous, so that if we do the calculation and then realize that it's not discontinuous, then that means the assumption was wrong. So we need to calculate for IA by using TE is equal to KM IA. So this is IA, right? So we now come here and then use the discontinuous current formula, which is this one. So we already know this is a constant, so we can calculate that constant. We know everything is given to us, so we can calculate for that constant, which is given by this relationship. So after getting that constant, then we now come back and replace the whole of this with the constant, right? That is how we go about solving this particular example. Do we understand? Because TS is a period, and we know that period is equal to 1 over F. So that is where this 1,000 is coming from. The frequency is 1,000 hertz. So that is where this is coming from. So we get Km. So you can substitute. So we get change in IA will be equal to what? 10 into 1 VDC over EB minus 1. So you have this relationship here. So that is what we are going to have here. But we already know IA to be what? 8. So we do the substitution. So you have 8 to be equal to 10 into VDC over EB minus 1. So we can make this the subject. All right. So you make EB the subject. So VDC is 400. So you make EB the subject. So when you do that, you're going to get this. And with this relationship, you can get a speed. Right. So we've obtained we are saying we have to calculate the new speed. Right. But we still haven't proved whether it is discontinuous or not. So we have to also prove that. So we have to also prove that, right? So we are now coming to prove for the discontinuity. So the change in, we realized that this was a change in current. One of the formulas that we saw, this was a change in current. IA, change in IE, this was one of the formulas. So we can make use of it. This is the current you are going to have. So this is the current we will get. And this current is average, right? So this current is going to be this isn't the average. The average current is from here. The average current is what? 8 amps, but this is the change in current. So the waveform, when you draw the waveform, like, so this is the minimum, this is the maximum. So the difference between the minimum and the maximum is given by this. And the average value is 8, right? So half of this is actually about 9. Okay, it's about 8 point something. So if the average is 8, that means that it's almost hitting the 0 line. It hits the 0 line, right? So from here, we can say that it is from this, with this one, you can even say that it is continuous because this value is more than what you get 8.5 something. So which is even more than the average. So when you measure from here to down here, you see that it has crossed the 0 line. So it is discontinuous. So just by looking at the current. But you can also use the time to check. So if you are using the time to check, we know how to obtain T2. So we know how to obtain T2. So we calculate for T2. T2. So we calculate for T2. This is what you are going to get. Then you also, that is with these are the what's the name? We had this one, and then we had this one. So we use them for the calculation. So that is what we are going to do. So that is how you go about solving the particular example. So yeah, you see here they are using IA, right? And we know IA is what? VDC minus EB over LA multiplied by what? This is changing IA. So when you make this a subject, so when you make this a subject, you're going to get T2 to be what? LA IA over EB, right? So you can, wherever you see change in IA, just put this one there. And realize that LA cancels LA. And you end up with VDC minus EB over EB multiplied by that. So you can either use this one or you use the one I quoted earlier to calculate for the T2. So you calculate for T2 with the parameters, you're going to get this. Then T2 is also equal to, we saw another expression that is equal to Ts minus delta Ts. So when we do that too, you will get this. So you realize that this time is what? Longer than this one. So that means that it will enter discontinuous mode before. So this will lead to discontinuity. So when you draw the waveform, instead of it to stay for like instead of it to stay for 500 microseconds, it will stay for what? 400 microseconds. So the other 100 microseconds, it's going to be discontinuous. So you can use the current or use the time to prove that. That is how you go about solving the B part of the question. And then the C, we are told that we should assume, let me go back to the question. We're told that for this condition in II, determine the duty cycle required to bring the motor speed back to the rated value. So the speed that we calculated here, we are saying that we should maintain the condition. So the torque is still the same. Right. So we want to change the duty cycle to ensure that the speed is the same speed here. So the only IA is going to be the same. EB minus, the EB value that we got here will still be the same. But the only thing that will change should be what? The EB will change because we are trying to, the speed should be equal to this one. So EB should change, right? So what we will only keep is what? The IA. So that is what will happen here. So EB will be the same as the first one. IA, we know IA already to be 8. So calculate for our K value. And we also know that K is equal to this. So the only thing that is we are looking for is what? The duty cycle. So you make the duty cycle the subject, do the substitution, and then you are going to obtain this. Any questions? Please, do you have any question on this example? I think this is the last example on the chopper drive, fed drives. Okay, so if there is no question, I think that's it. So you can go and read this, and then if you get time, maybe we'll do the control drives, the controllers. So I'll also try and then get more examples. We'll solve so that it's not like we are going through the slides again. So we'll just solve more examples to understand the nature of questions we'll be getting in our medicine. Okay, so if there is no question, we will end here and then continue another time.
Thank you very much for your time.
Come.